Well, thank you everyone for joining us today. I brought you all Steve Deveral, and I'll let him introduce himself because he has an extensive background on the Delta. But I wanted to let you guys have the opportunity to learn from him just because we all work very heavily in the Delta, specifically like with subsidence to a degree. So I want you all to ask him all the questions you guys may have that impact your work one way or another. And yeah, just let me know. I printed off this, but I'm also going to send it off to you in an email in case you guys want it as a digital version. And with that, do you guys want to do a quick round of intros and then we'll leave you for last, Steve, so we can learn more about you?
Okay.
All right, Mackenzie, do you want to kick it off?
Sure, I can put my face in here real quick.
Hi, Steve.
Hi.
I'm Mackenzie. I'm Restore the Delta's Youth and Outreach Program Manager, so I help oversee our ongoing outreach efforts here throughout Stockton and the Delta, and coordinating our climate water advocates along with Spencer, who is out water quality testing today. Pass it to Esther.
Hi, Steve. Nice to meet you. I'm Esther. I'm the carbon policy analyst here at Restore the Delta. Alongside Davis, we are working on carbon sequestration projects, especially geologic storage. So this makes me very interested in understanding how land subsidence might affect like geological storage projects. Thank you so much.
Thank you.
Hi, Steve. It's Artie Valencia. I'm the Flood and Land Restoration Manager here at Restore the Delta, and have a keen interest in learning more about subsidence just because of how it relates to what's going on with the levees in the rural Delta and how it's related. I have working knowledge on it, but would love to learn more.
And I'm Christina Pokley. I'm Restore the Delta's administrative assistant. So while I'm not behind the scenes like they are and you guys are, I'm still curious and want to learn more about the world of the Delta, since this is all new to me. So I'm really excited to have you here with us.
Thank you.
Hi, Steve. My name is Cynthia Cortez. I'm the policy analyst with Restore the Delta. I'm particularly really excited for today's training because just last week I went over to Sarah asking her a question about subsidence for a bill that's currently being proposed in the legislature. So I'm really excited to learn more from you today.
Thank you. Good to meet you all.
Sorry, I'm driving today. My name is Ahmad. I work with Restore the Delta in a couple different ways. Also work in agriculture. So really happy to learn about what you are bringing today. Pardon the background noise.
Thank you. Good to meet you. Good to meet you all. So,
Yeah, take it away, Steve. This is, did we make you a co-host? Let me see.
yeah, it should be. I'm going to share my screen. Yeah. So let me know if you see it okay.
Okay.
All right, let me put this on presentation mode. So you should be seeing, yeah, that coming across okay?
Yes.
All right, very good. Okay, well, thanks so much for the opportunity to speak with you about subsidence, and I added the restoration to it. I think those go hand in hand in the Delta these days. We can't really mitigate subsidence unless we work towards some kind of restoration plan. So I was out on Sherman Island last year at the Whale's Mouth wetland, which is the picture shown here. And it just was interesting to me as I took this picture looking towards the Antioch Pittsburgh industrial complex, mainly because I lived near that and my father worked at the U.S. Steel plant in the 1950s and 60s. And it just seemed kind of poignant that here I am standing in this restored wetland where we've basically accreted wetland organic material, and we've reversed the effects of subsidence. And it reminded me that something was written in Cadillac Desert many years ago, the book by Mark Reisner that talked about the go-go years, and that was the 50s and 60s were all about that, building the infrastructure for water in California, but it's also about mining peat, right? So the Delta was seen as this great agricultural area, and since the 1850s, we've lost 2/3 of the peat material that accumulated during the last 7,000 years. So during the last 7,000 years, almost 8 billion cubic meters of peat accumulated in the Delta. And since the 1850s, we've lost 2/3 of that. So we've really mined the peats, as we've mined other things. And I come from a long family line of miners, but certainly it seemed to me poignant in the sense that we're moving away from mining and going towards restoring. I guess that's the message that came to me from this. So just to kind of start out with that, I've been working in the Delta since graduate school back in the 1980s. I did my PhD dissertation in soil science at University of California, Davis. Had the privilege to work with agricultural extension specialist Alan Carlton in particular, and Blaine Hansen, who both worked on peat soils. Alan Carlton worked for decades, since the 1950s. So I really had the opportunity to work with people that knew a lot about subsidence and all the other processes that operate in the Delta. I joined the U.S. Geological Survey in 1984, and within a few years, I was back working in the Delta on subsidence-related issues, and really have continued on with that work even after leaving the Geological Survey in 1994, starting my own business and working with various entities in the Delta to try to work on understanding subsidence, understanding water quality, the hydrology of islands, and trying to develop mitigation strategies. So let me just kind of dive into this a little bit and tell you what's on my mind to talk about today. And please, if you have a question, feel free to interrupt. Please, please interrupt if you feel like you have a question to be answered. I will pause periodically to open it up for questions, but I'm posing a bunch of questions to try to answer here today. What is subsidence? How did we get to where we are today? How do we measure it? What are the consequences of subsidence? And what can we do about it? So it gets at this issue of restoration. How do you mitigate for subsidence? How do you get back what was lost? So let's talk about just let's talk about a few visual images of what it is. So this is a photograph that I took a few years ago from looking up at the San Joaquin River ship channel on Quechua Island and looking towards the levee. So I'm about 23 feet below sea level. And so I'm looking up at this boat, and the draft of the boat is, of course, above my head. So it gives you a little bit of a perspective on what it's like on these subsided Delta Islands if you've never been to one. It's kind of a dramatic thing to look at. I mean, I've been looking at it for much of my life, but people have never seen it before, kind of get this perspective. Oh, that's really, because at one time, the land surface elevation was up here, near the water level in the channel. So we've lost, 23 feet since this island was reclaimed in the late 1800s. I don't like the word reclaimed so much. It was drained for agriculture. So that's one vision of it. Here's a couple more. Here's a vision of Sherman Island subsidence. These power poles, which no longer exist on Sherman Island, were built in the early 1900s, 1910. And we, as part of the U.S. Geological Survey, went out and surveyed the land surface elevation at these power pole foundations. So we knew what based on the specifications for the building of these towers, we knew where the soil surface was when they built them. And then we were able to survey and determine how much soil had been lost. So you can see that in this graph here, that the average soil loss ranged during that time, ranged from 3 feet all the way up to almost 8 feet. So a lot of soil loss on Sherman Island as well. And then this is always a good thing to think about in terms of the perspective of subsidence. Walter Weir was a University of California extension specialist back in the 40s, and he actually developed these transects, these surveying transects across Bacon Island, Mildred Island, and Lower Jones Tract, which were right in the middle of the delta. And he surveyed them starting in 1922 and did it every year, almost every year, up until 1948. Yeah, there's skipped a few years here, but you get the idea, this downward trend. You look at Bacon Island, which was actually reclaimed in 1915. You go from -3.5 all the way down to -10.5 in that period of time. So really pretty substantial subsidence in the central delta where you have the highest organic matter soils. And there's some really good quotes here that were, this is 1950, the land subsides, the differential between the water level and the sloughs and the land surface on the islands become greater. This increases the pressure on levees and in turn tends to increase the seepage through them. And then he goes on, the destruction of the peat on the central portion of the area is, however, more significant than in the peripheral areas like Sherman Island. The central delta islands are already 10 to 11 feet below tide level, and greater lowering will therefore place considerable strain on the levees and materially increase drainage problem. This is prophetic, as you'll see in future slides. And so, how did we really get here? This is the elevations, the 2017 elevations for the Delta Islands. And you can see that these are in meters, but, these red, orange areas are -7, -6, so you're looking at, for the most part, over 15 to 20 feet below land surface in much of the central delta here. So, this is where the Weir transect was across Bacon, and then here's where Mildred Island was. This failed in 1982, and then on Jones Tract, which failed in 2004. So yeah, Walter Weir had some prophetic knowledge there. So let's talk about how these peats accumulated. This is one of the parts of how we got to where we are today. So we had this marsh accretion that took place in the delta during the last 6,000 to 7,000 years. And basically, you had this sea level rise that was occurring during the Holocene, during the Holocene geologic period. And what happened was, because the sea level was rising, it kept the plant biomass in anaerobic condition, which caused them basically the biomass not to decay very fast. You can see that it's anaerobic decay. And so that resulted in basically this vertical accretion of the land surface. It didn't happen very fast. So we're talking about a couple millimeters per year. But over 7,000 years, that's a lot of peat. And so this is what I'm talking about in terms of the Holocene sea level rise. You look about 10,000 years ago when the Holocene started. And basically, it was a global warming period after the Pleistocene, after the last ice age. And so you had this rapid sea level rise. It really started west of the Golden Gate, out in the Farallon. So that's where sea level was back then. And then it rose very quickly, but then slowed down as it arrived in the delta. So you had this fairly rapid sea level rise, and then it slowed down in the delta. So you really had peat accumulation because of this water coming into the delta, creating this plain, this marsh, where wetlands plants could thrive. And so it started about 6,000 years ago, as this line indicates. And so this is more of that. We actually, with the USGS, Judy Drexler and others, took carbon-14 samples of the peat. And you can see here that some pretty old stuff out there. But we actually developed or used a model to simulate this increase, basically this linear increase with time during the last 4,500 years on this particular wetland, which is just north of Frank's Track. But you can also see the fraction organic matter. So you're talking about 80% organic matter, but it varies substantially in the profile because of varying degrees of mineral material and sediment transport and such. But you get into the gold rush area, gold rush time frame, which is about here. This is about 1850 right here. You get this decrease in organic matter fraction. So we get all this mineral material flowing into the delta from the hydraulic mining that took place in the gold fields. And we're still kind of backing away from that. If you look at this, the organic matter starts to increase over time, but there's still a fair amount of sediment in these, at least in the channel islands, that reflect that. Let's just give you a sense of how things have accumulated out there. And this is what it looked like. This is a good publication if you're interested in historical ecology and what things look like. So you can see basically it was tidal wetlands. You had this vast expanse of tidal wetlands in the delta. And this is a USGS surveyor kind of showing you the tules, mainly tules that were predominant in these tidal wetlands in the delta. And this is one of our cores, just to give you a picture of what it looks like. This is probably 3,000 to 4,000 years old. But you can see remnants of the vegetation that are still there in this light brown material. So it's a really anaerobic environment that preserves that wetland vegetation.
Hey, Steve.
Yes.
I think Ahmad had a question in the chat. Let me see.
Oh, okay. I missed that.
No, it's okay. I can read it for you. So Ahmad said, you said tide level earlier, if I heard correctly. What's the difference between sea level and tide level perspective measurements?
Oh, good question. I would basically say they're equivalent for purposes of our discussion today. Yeah, Walter Weir used tide level, and basically I think that, they were still kind of going through the whole surveying process then, and he actually changed benchmarks in 1929 because of the official benchmark. So, and that was relative to sea level, but I think before that, maybe he used tide levels based on his understanding of the system at that time. But I think you can reasonably assume that tide level is sea level. So this is a map of the delta. So this is looking. The one on the left is looking east to west, west to east. Sorry, and you can see this bluish green area is all the tidal wetlands that were out there back then. So most of the delta. I mean, here's where Sherman Island is today, and move up into Twitchell Island here. But then we overlaid that with the soils map for a publication we developed in 2016. And you can see basically these high organic matter soils are all overlaid where that tidal wetland was. So that's really where all these high organic matter soils came from that are subsiding over time. And so it's basically this transition from, you can really see the difference between the tidal wetland that were in the Delta prior to the 1850s. And you see a lot of these dendritic channels going on to the islands, but you can see the outlines of islands in many cases here, like your Staten Island, for example. You can see basically the natural levee that surrounded Staten Island. Same here on Twitchell Island. And then you go to the modern situation where this color is all agricultural, and all these dendritic channels pretty much have disappeared. You basically got agriculture on all these islands that really changed the whole dynamic of water flowing in the delta and habitat as well. And it really started with this. Back in the early 1900s, they developed the clamshell dredge process for building up levees adjacent to these islands, using basically material from the channel, and created the levees and drained the islands for agriculture. So this is a diagrammatic illustration of what happened. Basically, now you've got a drainage system on the island. Instead of anaerobic conditions, you've now got aerobic conditions. So you have oxidation of this peat that's microbes just love to oxidize and generate CO2. There's compaction as you drain the soil. The peat dewaters and collapses on itself. There was also, and Walter Weir talks about this in that 1950 paper, there was wind erosion because there was a lot of asparagus being planted in the 1960s. There was a lot of burning, in particular, for potatoes and sugar beets. They felt like they needed to burn periodically to control weeds and root diseases as well. So these are the primary factors that led to subsidence, but the big one is the microbial oxidation. Once you expose these soils to oxygen, they disappear and oxidize. And so these are, again, this elevation map. But I wanted to show you a little bit of data from Bacon Island, which kind of illustrates the processes a little bit more clearly. So this is some work we published in 2010, which basically shows, we were fortunate to have all the notes from Walter Weir's and his colleagues surveying. So we were able to go back to his survey transect on Bacon Island. So they stopped measuring that transect or elevations along that transect in 1978, which is represented by this dot, if you can see that. And then we redid that transect in 2006. So we got a pretty good time series of what subsidence looked like, or what average subsidence looked like along that transect on Bacon Island. And then we were able to develop a model, what we call the subcalc model. So you can see the percentages of the different causes of subsidence during this time period. So almost half of it was the result of oxidation. We know that there's no burning going on today, which would be this, and the wind erosion is minimal. Once they stop planting asparagus on these soils, the wind erosion has really decreased over time, also as the organic soil has become more dense and less organic. So there's less influence of the wind on blowing these soils away from the islands. But during the 1960s, it's been said that there was so much wind erosion in the delta that it would accumulate in Stockton, where you are. So there's a lot of wind erosion that carried peat all the way into Stockton back in the 1960s. And so here are some of the factors that Stevens et al. Point out in this man-induced subsidence book. For example, in several places, you can see the relationship of subsidence to depth to groundwater. So it's been known for quite a while that the deeper the groundwater, the more subsidence you have. And that's really because the mass of peat that can oxidize is much greater And so there's more microbial action that can take place to oxidize that peat. And so in Florida, for example, you have this really nice relationship between the average depth to the water table and the average subsidence rate. Indiana and the Netherlands as well. And then there's a temperature. The higher the temperature, the higher the oxidation rate. And so he developed basically this graph for the annual subsidence rate related to the soil temperature and the depth of groundwater. So deeper groundwater, higher soil temperature, higher oxidation rates. So not much had been done in the Delta at this point in terms of trying to figure these things out. Stevens was really kind of a pioneer and working in the Everglades and really developed a lot of the concepts that were helpful in the Delta. But we do see this relationship of subsidence rate to fraction organic matter that he also points out in his work. So this is the Sherman Island data from the work or the measurements I showed earlier. So this is this correlation of fraction organic matter with subsidence rate and for Bacon Island as well. So the higher the organic matter, the higher the subsidence rate. And so it's kind of a vicious cycle in the Delta under current baseline conditions, and that you have this oxidative subsidence that reduces that mass of organic soil above the water table. So you have to deepen your drainage ditches to maintain that aerated root zone. But that increases the oxidation rate again because you're exposing more peat to the oxygen, which results in the need to reduce the drainage depth again. So you kind of go in this vicious circle, continuing to deepen drainage ditches. And there's some consequences of that. I would say at this juncture that I've had some interactions with folks that are actually putting in, so all the drainage ditches that I've been involved with are open drainage ditches. And I think there's probably good reason to keep them that way. If you start putting in buried drainage lines, which they are doing on some islands, you can realize that you haven't got the freedom to go back in and deepen that drainage ditch because you've got basically a buried drainage line in the bottom of the ditch that's going to get shallower with time. In other words, the depth of that drainage line relative to land surface is going to get smaller. So I've talked with a few people about that. I'm not sure that's always recognized. So how do you measure this? There's really three methods that have been used. I'll talk a little bit about those. Surveying is one. We've talked about that. Where we resurveyed those. This is Dave Layton from Hydrofocus, and we basically resurveyed those 1910 power poles on Sherman Island and compared those with the data that were reported earlier. And you can see the differences there. So all those subsidence rates, for the most part, most of them had decreased from the 1910 to 1988 that was shown earlier, from 1988 to 2006 when we surveyed these in 2006. So that's kind of a good reminder that because the organic matter in these soils is decreasing over time, the subsidence rates are tending to decrease. However, there is a temperature process there too, and as global warming increases over time, the temperature of the soil tends to increase as well, which can kind of balance out that change in organic matter content. So that you have to take that into account where you look when you're trying to predict future subsidence rates. And so this is another way we measure subsidence, which is an extensometer. Basically, we put steel pipe into the ground below the level of the peat, We have steel plates that, these are the steel poles that are driven into the ground. We have a displacement detector on a platform that sits on these steel poles, and this records the change in the land surface elevation over time. Basically records that land surface elevation. And so this is what that looks like on the ground. This is actually one that was developed in Italy. We were the one, Stuart Roystatzer really at the USGS built the first one that was placed on Sherman Island, Orwood Track, and one other island, which I can't remember right now. But we set up something similar to this, but didn't look as nice as this picture did. But so I wanted to show this because it really illustrates this whole process. So you've got this basically this instrument that records how this plate that sits on the ground moves downward over time. And this, of course, is anchored below the peat and gives you data for how fast the land is subsiding.
Hey, Steve.
Go ahead.
Sarah had a
Yeah.
question.
How far apart are those? Like, I guess, how big is that?
This is probably about the same size as we made them. So these are probably 6 to 8 feet long, something like that.
Okay.
Yeah, it's pretty small. Yeah. So these are some data from an extensometer we had on Twitchell Island. And you can see there's some important things to recognize here. So the red is basically the extensometer change in land surface elevation. So we start out at 0, and then we go down, we come back up a little as the groundwater levels come up. The blue is the groundwater levels. And then it goes down, come back up, but not as far, goes down, come back up, but still not as far. So you look at the overall change in land surface elevation, it's about 5 centimeters during this period from 2009 to 2013. And these are our manual measurements too. We always check those manual measurements. But it shows you something really significant about these peats, and that there is an inelastic, what we call inelastic subsidence, where we're losing peat and we're losing ground. But there's an elastic part of it too, because the peats are so light and buoyant that when the groundwater comes up in the fall and winter, you have this rising of the land surface elevation. So you can see that in the data. So you always have to take that into account when you're measuring subsidence. You can't that's why it's hard to take just single measurements over a short period of time, because this change in groundwater levels has to be taken into account. So this is a new way of measuring subsidence. It's just come about within the last decade or so, a couple decades. It's basically, this is a satellite radar signal that gets basically sent from the satellite to the Earth's surface and then bounces back. So you basically measure the time frame for this sending and receiving to occur, and then you do it another time, and you can see the difference between in the time it takes for this signal to move towards the Earth's surface and comes back. It's very delicate and can be very accurate. So in this case, there was an increase in the Earth's surface, and this is the synthetic aperture radar on the satellite was able to pick that up. We've done this in the Delta. The big deal for the Delta is what we call coherence. So if you're going to do this multiple passes, you have to have a fairly stable land surface. In other words, if somebody goes in and plows the land between the readings or through the signals, you're not going to get a very good very good data. You're not going to get data that's really worth anything. So it's just basically what we call correlation that's problematic. And the Delta environment presents really significant challenges for the use of satellite synthetic aperture radar because of that. Now we have cooperated with NASA and Jet Propulsion Lab to do it airborne, which has been a real gain for the Delta and other parts of California too. It's being used all over California now to measure subsidence in the Central Valley. And we've collaborated with JPL on this particular project back in 2009, where they started making monthly flights. And we compared those data to the extensometers we operated on Sherman and Twitchell. So this is kind of what it looked like. They did passes both this way and this way. Here's Sherman Island here, kind of looks like a whale. That's why they call the wetland that's here the whale's mouth wetland and the whale's bellies wetland. And so basically they were able to estimate the subsidence rate at a pretty fine level on Sherman Island as a result of this. It's about every 7 meters or so. But it's not as precise as one would hope. And there were some problems with actually predicting subsidence where there's probably accretion on Sherman Island. There's still some kinks to work out on this process in my mind. We're actually talking with JPL and NASA about doing more frequent flights, which, excuse me, which may be a good thing for the Delta in terms of measuring subsidence at a larger spatial scale than we're able to right now. But you can see this comparison with our extensometer on Sherman Island. The subsidence at the extensometer is pretty tight here, but you see these readings from the airborne UAV SAR, and it's not as tight. And that's because of the correlation. There's also some issues with being able to benchmark a lot of these measurements. There's also LiDAR. DWR goes out there and it's basically light detection and ranging. It uses light in the form of a pulsed laser to measure angles and variable distances to the Earth. It's got 9 to 18 centimeter accuracy, which means you really have to wait a decade or so between readings to actually get enough of a signal that you can actually look at what the subsidence is in the Delta. But drone LiDAR is becoming more popular, and it's got about 5 centimeters accuracy, so you could probably use it in areas with more frequent flights. And it is being used to measure elevation. I'm not aware that it's being used anywhere that Delta to actually measure subsidence rates. So this might be a good place to pause and see if there are any other questions or people need to take a sip of water or something like that.
Any questions?
No, not yet.
Interesting.
Ahmad might have a question.
Oh, he's got his hand raised, doesn't he? Okay, very good. Go ahead, Ahmad.
Okay, thanks. I'm still out and about, sorry.
That's okay.
I'm wondering because one thing, shoot, and I'm sorry already for the language. Hopefully you can piece it together.
Yeah.
In terms of like carbon sequestration in our area, like tidal estuary, super granular, but even like maybe one layer out from that, just the Delta itself and subsidence. Erosion is a huge issue across the Delta. And now I'm starting to understand this may be one of the key factors and why it's such a huge challenge. I know also wind erosion is a big piece too. But I'm thinking in terms of carbon sequestration in wetlands, because straight up the Mormon Slough restoration, work that we're doing. And just wondering, number one, if you can create a through line, or if you see a through line there. I feel like there may be some connection in terms of like implementation outcomes. Like, is there an intersectional space where carbon sequestration can nestle up to subsidence solutions?
Yeah, I think that's definitely, I think, where we're headed in the Delta on these islands. We've, and I'll talk more about that. But I think it's a really important topic. Well, just in brief, because I'll get into more detail about carbon sequestration. It's really the benefit of creating wetlands in the Delta is really the stopping of subsidence and reversing its effects. So what we found on the wetlands that we've created, first one was in 1997 on Twitchell Island. And there's definitely carbon sequestration that occurs there. There's also methane emissions, which can offset that carbon sequestration. But the bottom line is that you're putting wetlands on the land, you're keeping that soil anaerobic now. And so basically you're stopping that oxidation that it results in the subsidence. So even though there's the wetland itself is probably a very small source or small sink, the fact that you're stopping that baseline emission can really make a huge difference in terms of emissions reductions in the Delta. Just to throw out some numbers, we estimate that the Delta loses about 1.2 million metric tons per year of CO2 equivalents, just because of the oxidation of these organic soils. And so if you create wetlands and stop that, basically that's the emissions reductions. I mean, let's say the wetland, which is typical, is a net source because of the methane on the order of maybe a ton of CO2 equivalents per year. That's really small in comparison to the emissions reductions that happened as a result of creating that wetland. Not to mention that it accretes probably 1.5 inches a year. So it really reverses that effect of subsidence. That makes sense?
About 80% for me, but I'm just in that space. But I do know for sure that is a wonderful answer. It was very illuminating. I already have like stuff to look into now. So
yeah.
Well,
there's more. Yeah, great. And I'll be saying more about that too. The carbon's a big part of this. So any other questions at this point?
Yes, I have a follow-up question on sequestration, but more on the side of geological sequestration. I'm curious about how and if erosion and or flooding has an impact, in your opinion, on subsurface formation. So like a significant impact, because one of the projects I'm working on, I'm considering whether any form of like significant erosion, like the weight of the overburden, the pressure, the weight of the land will like significantly, like the weight of the land caused by erosion or flooding will significantly affect, or subsidence would significantly affect the subsurface. I think is my question, in your opinion.
I'm not sure I understood all that. So are you asking about the overburden that might be the result of erosion that would also exacerbate subsidence? Is that the question?
Yes, my question, yeah, whether overburden will change significantly as a result of erosion or as a result of subsidence.
Yeah, I see what I think I see what you're saying. Yeah, that's an important issue, especially when it comes to levees in the Delta. So when you build levees in the Delta, there is this overburden, and you do consolidate that peat for sure. And that's a process that's that really is important. I mean, basically, you put about 5 feet of mineral soil on the peat, you're going to lose. That's going to consolidate at least 50%. So, and probably more. So you have to do when they build these levees, for example, you have to do it in successive lifts where you put the mineral material on the peat soil, it consolidates, and you put more on. So it is a factor that's important. In terms of erosion, I'm not sure how that plays out in the Delta really, because all these islands are so flat. I suppose if you had areas where you had erosion coming from upslope, that could be a problem, but I'm not aware of where that would be the case in the Delta.
Thank you so much for clarifying that.
Sure. All right, well, let's talk a little bit about effects. There are 3 main effects that I'll talk about. I think they're the primary ones. There's decreased arability or decreased ability to farm on these islands because of subsidence. The levees and the water supply have become more vulnerable over time, and water quality is affected by subsidence. So we did a looking at one of the things I recognized when I first started working in the Delta was in the 1980s. You drive, I worked on a dozen islands when I was doing my research, working for agricultural extension. And you just didn't see all that many areas that they weren't farming. But then fast forward a couple decades and continuing to work in the Delta, I noticed a lot more areas that were being abandoned, were not being farmed. And so we tried to use basically satellite imagery to quantify that. So we took images starting in the 1980s and went all the way through 2012 and found that what we call the wet, non and marginally farmable areas increased over time, about tenfold actually. And this next slide shows an example of that on, oops, sorry. This is on Golden Island. So you can see this increase so back in the 90s, most of this area was still farmed. And then you go to 2002, less of it's farmed. And then you go up here to 2012 and 50 hectares is not farmed here. So this is an area of a couple hundred acres that has turned basically into wetlands because basically the land gets too wet to farm. And what happens was, I've talked to a few growers and landowners about this, is that once the land starts to get too wet, machinery gets stuck, and it usually happens in the spring. It may dry out during the summer, but because they can't get machinery in there, they start staying away from these areas, and that causes basically the area just become a wetland. And so it results from this. This is somewhat of an exaggerated point of view, but back in the early 1900s, we had very short levees, not wide, and they protected the islands. But there's a really small hydraulic gradient onto the island from the channel water to the drainage ditch. There are always these toe drains at the toes of levees that collect water that seeps through the levee. But as subsidence occurs over time, you've lost a lot of this peat, And now it looks more like this, where you have really high levees. They're constructed to stay stable, so they have to be wide. There's a lot of fill material on them, but there's also much higher hydraulic gradient, which is the difference between the water level in the channel and the water level in this drainage ditch, that causes water to move through these ditches, which is through seepage, which is fairly easily, or can be controlled relatively easily. But what happens is a lot more water flows underneath the levee. And so that means it moves faster, because these are not organic materials. They're sands and silty sands that transmit water pretty fast, to create situations like this, where you have a high water table that's a result of these higher hydraulic gradients. It also creates problems from a seepage force on the levee too, but this seems to be the primary cause. As subsidence decreases, this hydraulic gradient increases, which causes the drainage ditches not to be able to remove water as fast as it comes onto the island. And I've talked to a number of landowners and growers about this, and I was talking to the farm manager on Venice Island, where they have a lot of this going on, and he said, you just can't get the water to flow to the drainage ditches. They would put new drainage ditches in, and they couldn't control this. And I think part of that is because you have water that's close to land surface, you have a much higher evaporation of that water, and the water prefers to evaporate into the atmosphere rather than flowing to the drainage ditch. So in terms of levees and water supply, the seepage forces are an issue. Slope instability and levee failure. There are really kind of these ongoing problems with delta levees. What we learned, well, let me just talk about this slide for a minute. So basically, we've got all these highly organic soils surrounded by levees that are overlying those original, for the most part, original levees that surrounded the island when they were tidal wetlands. We've got basically levees that are called levees, but really they're more like a dike. They have to hold back water 24/7, and it's more like a dam without a spillway. So levees, by definition, are really something that holds back water during high water events. So that's an issue for the Delta, because 24/7 you've got to have something that holds back water. So there are these forces that compromise that. And we know that the Delta is basically the key element in terms of transferring water to Southern California. As illustrated here, we have 18% of the water that goes to the State Water Project or the Central Valley Project. Most of it goes out to the ocean, but still, the state's water supply depends on moving water from the northern part of the state to the southern part of the state. So when levees fail, there is this potential that this can be interrupted. And there have been, since 1950, over 80 failures on Delta Islands. Most of them associated with high water events, as illustrated by these peaks here, and on multiple levee failures during really wet years, but some not. And just to talk a little bit about slope stability, this is a diagram I borrowed from Chris Enright, who took Kevin Tillis is a geotechnical engineer, has done a lot of work in the levee, and he described it like a teeter-totter. So basically, you got this cohesive resistance moving against the force that wants to allow this levee to move towards slipping. So it's kind of like that. So if the cohesive resistance isn't strong enough, you have this slump in the levee. And when this inboard side subsides, you have greater tendency for this levee to slip and slump. But there's also the seepage force, which I talked a little bit about already, but it depends on this exit gradient, which you don't have to get into the details too much, just to realize the water in this aquifer underneath the peat is higher than the drainage ditch, which means that there's a force that is forcing this water into the drainage ditch, which can be strong enough to begin to move these materials that are underneath the levee into the drainage ditch and cause what we're known as boils. So basically, this is a boil that we observed on Jones Track. This is after the Jones Track failure in 2004, but it was also seepage forces were actually cited as a likely cause of levee instability on Jones Track in the 2004 failure. So you see in this diagram a little bit more explanation of that. So this relative probability of failure is related to basically the factor of safety. And so it's not really a relative probability of failure in any given year. It's just basically an index of how vulnerable the levee is for different marsh deposit thicknesses and levee height. So you have this, the higher the levee, the more vulnerable it is to this slope instability process that I showed earlier. And the thinner the marsh thickness, and we say the marsh thickness is basically the peat plus the tidal mud that's underneath the peat that first formed when sea level rose into the delta, you've got this exponential relationship. So the thinner the peat gets, the higher the relative probability of failure. And that could lead to boils like this. You can see that mineral material that's underneath the levee kind of flowing into that peat, that drainage ditch, toe drain as we call them. You see this periodically in the delta. You have to go in and put sandbags around it to try to equalize the hydraulic force and stop this erosion of levee foundation materials. But the Delta Risk Management Strategy Project stated that this is kind of a slow acting force on delta levees that can reduce their stability over time. So we've had a couple examples of pretty serious levee failures in the delta, which are exemplary of the effects of subsidence. I should say that the literature indicates that really it was after the 1940s when levee foundation instability became a greater process for levee failures because of subsidence. So it's really over the last half a century or so that we've been, or maybe 70 years, that we've been looking at levee failures that really are the result of subsidence. And we've done a tremendous job of upgrading our levees since the 1970s to compensate for the subsidence that has caused levee foundation instability. But the Jones Track failure was somewhat of an extreme example. It happened during the summer. I remember I was out in the field that day and my wife heard about it and she called me, and I didn't know about it, but I was a few islands away and she was a little concerned that I was out in the delta. But flooded 12,000 acres, upper and lower Jones Tracks. We had to shut down the delta exports. Had to release more reservoir storage water. And the direct and total costs were estimated at over 100 million in 2018 dollars. probably the more important levee failure from a historical trajectory standpoint is the Brandon Annis failure that occurred in 1972. And this is a water quality effect. Because it's in the Western Delta, it's the big gulp phenomenon. So basically you have saline water that's west of Brandon Andros out closer to Sherman Island. But you had, during this failure, over 300,000 acre feet that moved onto the island. I'm sorry, over 150,000 acre feet that moved onto the island. And this resulted in an increase in the salinity of the water in the Delta, ranging from 2.5 to 4 times. So from that standpoint, because the water was too salty to export to Southern California, they shut down the state's water project. They had to release about 300,000 additional acre feet from Folsom Dam, from Oroville, and other, and the Central Valley project to flush out that salt. DWR estimated direct costs at 180 million in 2018 dollars. And there were local and statewide economic costs that exceeded 250 million. But this was the event that really woke DWR up and the state. They started investigating levee stability. They started looking more into subsidence. And there were several DWR publications that encouraged the adaptation of shallow water table adjacent to levees, or some alternate land use that would reduce subsidence adjacent to levees, and basically created funding, which was the subvention funds and later became special projects fund, that has spent over $700 million on levees since the mid-70s. And you can see it in the failures. We've had much fewer failures since then. Since the last few years in particular. 2004 was the last failure that we had in the Delta. But there's still an estimate of numbers in hundreds of millions to bring all these levees up to standards that the state would hope to have. So I've talked a little about the water quality effects associated with levee failures in the Western Delta, but there are other ones that are kind of related to what happens in these peats as water is applied and drained. One of them is dissolved organic carbon. I did want to show this island water balance, which I think got left out of your package, but basically just to give you an idea of how water moves on and off these islands. So basically we've got applied water that basically comes onto the island via siphon. There are siphons that go through the levee and bring water onto the island. I've indicated that just as an arrow here, that there's applied water for irrigation of crops, but these crops also use the shallow groundwater. Because it's so shallow, they can basically evapotranspire that water as well. And so there's seepage that comes onto the island, both to this area adjacent to the levees, but also to these center island drains. And there's, of course, drainage that flows off the island. So those are kind of the ins and outs of Delta Island water. And the dissolved organic carbon is an issue because of the drainage, basically. So this is the dissolved organic carbon concentrations at the Banks pumping plant in the Southern Delta, which takes water out of the Delta and transfers it to Southern California. And you can see these spikes every winter in dissolved organic carbon. They would like to keep it below 3, but you can see during the winter, every year it goes up beyond that. So why is that? The literature and research indicates that a lot of that spike in dissolved organic carbon is related to processes that happen on delta soils. So I'm just going to walk through this slowly. I know there's a lot of numbers here and a lot of chemical stuff, but I'll just try to keep it as simple as possible. So under drained conditions, so we've got a water table that's, you know, 3, 4, 5 feet below land surface. You've got a crop growing here. You're oxidizing the soil, but the water's flowing to the drain is primarily from groundwater. So that groundwater has a dissolved organic carbon of close to 9 milligrams per liter. And that's reflected in the drainage water concentration during May through November, low flow periods. So those are the periods where we see in that graph, in that previous graph, that we had these lower organic matter contents, lower dissolved organic carbon contents. So fast forward to December through April, we've now got high flow in the drains because water table comes up during the winter. Island drains have trouble keeping up with that. So the water comes to land surface. So now you're flushing out all this dissolved organic carbon. You look how high this dissolved organic carbon is, 80 milligrams per liter, gets flushed into the drain compared to what's in the groundwater, which is still that almost 19 milligrams per liter. That results in a dissolved organic carbon concentration in the drain of this 40.3 milligrams per liter. So that's where this contribution from the delta to those spikes in the dissolved organic carbon we saw at Banks, that's where part of that comes from. It also comes from the Sacramento Valley, where you have flushing of rice fields and that kind of thing, but 40 to 50% of it comes from the delta. Just from basically the continued oxidation of these soils, which generates dissolved organic carbon, gets flushed into the drainage water and flows off the island. You notice that this is indication of salinity, that this electrical conductivity, or EC, you can see it's also high as well. So that's a concern, can be a concern. And it says there, it's to note that salinity is really coming from the oxidation of the peat. As you lose the peat, the minerals stay behind and concentrate and generate salinity as well. Methylmercury is an issue on organic soils because of the hydraulic mining that took place. So you had this big flushing of sediment coming down the system in the late 1800s. Mercury is associated with it because mercury is used to extract the gold from the sediments, and it ended up on Delta Islands. You can see if you look at a profile of mercury concentrations in Delta soils, you see a pretty high level of mercury at the surface of the soils. So you can see the difference between organic and mineral soils. This is a study we worked on with folks from San Jose State. And you can see that in general, there's more organic, more methyl mercury coming off these organic soils. And it's really related to the dissolved organic carbon. It's kind of the same process. You've got this organic material, the microbes are oxidizing an organic material, and one of the ways they deal with that mercury is to convert it into methyl mercury, which flows out in the drainage water. And you may be aware that there's a limit on how much methyl mercury can be in these delta channels. It's pretty low. It's based on the fact that it accumulates up the food chain into fish. And so they set some standards throughout the delta for how much methyl mercury can be in those channel waters. And again, this average load that we estimated, we measured the drain flow as well as the methyl mercury concentrations, And these are the organic islands we studied, and these are the mineral islands. So this is Jersey, Staten, Twitchell, Bolden Island. All these have pretty high loads compared to the mineral soil islands. So another water quality issue. So now we get to the part that's a little more positive, I would say. Alternate land uses. Rice stops subsidence, managed marsh reverses its effects, as I mentioned earlier. These are a couple examples. This is a rice field on Staten Island that we've been working in. This is an eddy covariance tower that we operate. Basically, this is how we measure the carbon changes in these carbon fluxes, basically, in these land uses. And this is the Twitchell Island wetland that was created in 1997. This came out of some early work that we did, basically published in 98, but we learned from some mesocosm experiments that permanently flooding these delta organic soils really led to a net carbon benefit or net carbon gain relative to the net carbon loss associated with the organic soil. So it led to this 1997 pilot project of 14 acres in the middle of Twitchell Island. It was really the beginning of what's now 2,000 acres of wetlands on Sherman and Twitchell Island. And this basically shows the change in, this again, kind of an extensometer, but it's actually called the sedimentation erosion table, where you can measure land surface elevations over time manually. So these are our changes in elevation over time. The data is really not conclusive in terms of whether there's an increase, but certainly it's not going on a downward trend like we saw in that other graph for Twitchell Island. And it goes up and down with the groundwater levels, which are shown here in blue. And then wetlands, this is a 1997 wetland when it was first created. This is what it looked like a few years ago with all the biomass that's accumulated. And this is the kind of biomass that accumulates there. This is actually Robin Miller's foot, a USGS researcher. So you can see this fluffy porous material that accretes in these wetlands. And this is basically accretion over about 20 years, a couple feet of accretion in this wetland over 20 years, about 3 centimeters per year. And it's really this process. I mean, it comes out of this basic concept that I talked about earlier, where we had increases in sea level over time, and there's this long-term accretion of compacted intervals as a result of continual inundation of these wetlands. We tried to simulate that in this wetland, where as accretion occurred, we would raise the water level in the wetland to compensate for that accretion. So it always kept the biomass under anaerobic conditions, which leads to this accretion process. So how does that affect levee stability? This is a diagram that Sander Bershon developed. Oops. Huh. Let me reshare this. Something happened here. Wow, that's weird. Hold on just a sec. Looks like PowerPoint. There we go. There we go. Sorry about that. Oh, technical difficulty there. All right. So this is a plot of the cumulative reduction of annual probability of failure under business as usual in 2070 by applying rice or wetlands on subsided islands. So it does become a nature-based solution for reducing the probability of failure over the long term. So for wetlands, this was done for various islands, but it gives you a sense of some of the more subsided islands, like let's say Mandeville Island. You would reduce the probability of failure by about 25% by creating wetlands. Venice Island, all these central delta islands would benefit from a cumulative reduction in annual probability of failure by upwards of 50% for some of these islands, but probably on the average, more in the order of 30%. And rice stopping subsidence also reduces that cumulative reduction, or reduces that probability of failure over time. So one of the things we really kind of came up with in collaboration with the Nature Conservancy was, what if you could create, just to back up a little bit, one of the concerns, of course, is that you can't just create wetlands all over these islands where people are actually using agriculture to generate an income and pay for levee improvements and such. So on Staten Island, we tried to come up with a mosaic that would allow for continued income, but also reduce the greenhouse gas emissions and stop or reverse the effects of subsidence. So this is pretty close to what it's starting to look like today on Staten Island, where you have a large area of the southern part of the island that's planted to rice, and then a good part of the island that's actually being converted to wetlands. These are the highest organic matter soils in the southern part of the island, and and also the greatest greenhouse gas emissions are from this part of the island. This is a concept that was initially developed in 2015 or so, 2016. And it was after we wrote a report for TNC that was given to them in 2012 that suggested conversion to rice. And the manager of Staten at the time, actually the president of Conservation Farms and Ranches, DeWitt Seleka, who passed away not too long ago, he was reluctant to convert to rice for a number of reasons. But he said to me at one point, or said to somebody, he said, I'm going to prove Deveral wrong by planting rice. So yeah, they've ended up doing it. And I think they're almost up to 2,000 acres of rice this year.
Something to say.
And so let's talk a little bit about carbon, getting back to some of the discussion that we had earlier. So as I mentioned before, the emissions reductions with land use changes, and there's a potential for offset credits. So we learned early on that basically these numbers, which coincided with the measured elevation changes for the most part, were calculated from the carbon loss that we measured back in the early 90s, late 80s, early 90s at the USGS. So we knew pretty early on that subsidence results in a carbon loss. But there's much more sophisticated measurement techniques now. There's the eddy covariance that really has been developed extensively at UC Berkeley, which measures the flux of methane, carbon dioxide, and water through these analyzers that sit on a tower. And then this is the anemometer that measures wind speeds associated with the fluxes of these critical greenhouse gases. So basically, it's a three-dimensional anemometer that provides a flux of methane, flux of CO2, and flux of water. So you can use that to basically continuously measure the change in, or the fluxes of these elements from the land surface. So this, the combination of these data and conversations with the American Carbon Registry and the willingness of some entities to help fund the development of a methodology led to the creation of the methodology for quantifying greenhouse gas emissions reductions in the Sacramento-San Joaquin Delta. And it really was kind of two independent and parallel processes. And the idea was to create a mechanism whereby landowners in the Delta could hopefully convert to wetlands and still have some income associated with that in the carbon market. That hasn't manifested itself yet, but the carbon market's still quite young, and we're hopeful that this can happen over time. But basically, we tried to synthesize the available data for the methodology and utilized the best information we could, so the model could be used by producers for trading emissions reduction tons and CO2 equivalents. So there was ongoing data collection, analysis, and modeling. There were pilot projects, the Twitchell and Sherman Island projects. There were measurement of the baseline greenhouse gas emissions, and there was modeling that went into basically prescriptions or directions for a project proponent to follow to be able to basically have these carbon credits verified. And it looks something like this, where there are baseline activities which include agriculture, seasonal wetlands, and open water, and then project activities which include rice cultivation, which we know stops subsidence and in many cases provides greenhouse gas emissions reductions, manage wetlands, which reverse the effects of subsidence, and then tidal wetlands also. The open water was mainly areas such as the salt ponds in South San Francisco Bay that were targeted for this. So far, we've had credits that have been verified for this agricultural to manage wetlands. We have validated the project on Staten Island for this conversion of agriculture to rice cultivation and creation of managed wetlands, permanently flooded wetlands. Now, I would just mention here that the managed wetlands include what we call polluticulture. So polluticulture, I think, could be a benefit for the Delta. It's something that's practiced in Europe and Canada and other places where they actually take wetland biomass and use it for economic benefit. So things like particle board, roof thatch, medicinals are harvested from wetlands and can provide income for having managed wetlands. The protocol allows for polluticulture, and we're trying to see how that might work into the Delta. One aspect of that may be taking biomass and converting it to biofuels such as ethanol, which we're trying to explore as well. But it's noteworthy that these credits that were verified on Sherman and Twitchell Island, over 50,000 tons of carbon dioxide equivalents, were the first ever wetland carbon offsets. So nowhere else in the world had there been at that time verified carbon credit offsets. There have been some that have been verified since then, but we were really a pioneer in that respect. And I just wanted to kind of give you a sense of how this works from basically a carbon benefit standpoint. So under agricultural conditions, we've got this large emission of carbon dioxide because of the oxidation of the organic soils. We have under wetland conditions, the sequestration of carbon dioxide that goes into the biomass that accumulates as wetlands. But we also have methane that's emitted. Now, when you have methane emitted, you have to multiply it by what's called the global warming factor, which basically is about 30. So even though you have a small amount of methane that's emitted, it in terms of carbon dioxide equivalent, it's a fairly large number. So that's what I was saying earlier. So the difference between this number and the negative numbers basically mean that it's a net benefit and net emissions reduction. So the fact that you've got wetlands emitting methane offsets a lot of that carbon dioxide that's being sequestered. But the net is basically this number minus this number plus this number, which is about minus 9.2 tons of CO2 equivalents per acre. So it's really this agricultural emission that you're stopping that is really the big benefit here. And so getting back to the Staten Island mosaic, where we're going from a situation where most of the island was planted to corn, most of the southern part of the island is highly organic soils. We convert that to this situation. We found a 60% reduction in greenhouse gas emissions and a slight decrease in profitability. But we've continued to work with TNC and the San Francisco Estuary Institute to better quantify these numbers. And with the carbon market prices increasing and rice prices increasing as well, the profitability for a scenario which includes this rice wetlands, such as it is today, is actually more profitable than the corn, based on recent analysis. So it does provide some hope, I think, for islands where we do have a situation where we're subsiding and we can create possibly a mosaic like this, where the critical prioritized areas for conversion are those areas that are subsiding the most. So I've come to the end of my talk. We talked a little bit about what it is, what subsidence is, how did we get here, you know, that evolution from the accretion of wetlands over time. Talked about how we measure it using surveying and satellite, airborne data, as well as extensometers. Talked about the consequences, levee vulnerability, probability of levee failure, water quality, decreased ability to farm. And we talked a little bit about possible mitigation, in which we've been able to demonstrate that rice and wetlands can stop and reverse the effects of subsidence. And there are some possibilities for moving forward with that, albeit slowly on these Delta islands. So I think I'll stop there and entertain any questions.
Thank you, Steve. Do you guys have any questions for Steve today?
Not at the moment.
What was that?
Not at the moment.
Okay.
Questions, comments, concerns?
I understand. Was it evidence a little bit more?
Steve, one question, about subsidence and how it affects, pollution or the water quality of surface water versus groundwater. Have some ideas on that?
Subsidence due to groundwater withdrawal, is that the question?
Mhm.
Yeah, that's in a way that the process in the delta is the result of groundwater withdrawal, in that you're draining the water off that soil and it causes oxidation. But there's also subsidence due to groundwater withdrawal throughout the Central Valley because of pumping of groundwater, and it's a phenomenologically it's a different process, and that you've got basically extraction of water below these confining clays in the subsurface, and the extraction of that water below these clays causes those clays to dewater and collapse. It's a well understood process. The USGS has done a lot of work related to that, dating back to the 1950s, but it has caused a lot of subsidence in the Central Valley, up to 9 meters in the western San Joaquin Valley between 1920s and 1977, something like that. So there's this famous picture of Dr. Joe Poland standing next to a power pole and showing the 9 meters of subsidence as a result of that aquitard drainage process, basically.
Thank you for clarifying that. Thank you so much.
All right, well, if you all don't have any questions, Ahmad, I don't know if you have any questions by any chance, but if not, and anything comes up, we'll stay in touch. Steve, thank you again for taking the time for presenting for us today. I will be sending this out to you all, so you guys can see all of the pretty slides and color as well. And if you, is it okay with you if I share your contact information with the team?
Sure, yeah, that's fine.
Awesome. Well, thank you again. We really, really appreciate it, and stay cool this weekend. Thank you again, Steve.
Okay, thank you. Have a good rest of your day.
Awesome. Thank you so much.
You're welcome. Thank you.